Good day, viewers. So, welcome to another edition of NAMSSN tutorial. So, today we want to look at how to use Laplace transform to solve boundary value problem, partial differential equation. So, in our previous video, we've done how to use Euler method of separating variables to solve its equation, wave equation. So, today now I want to look at how to use Laplace transform. So, let's go back to definition of Laplace transform. We already know that Laplace of a function is equals to integral from 0 to infinity e minus st f of t dt. So that is the definition of Laplace transform of a continuous function. So now we want to look at partial differential equation. Now, how do we bring in partial derivative into the context of Laplace transform? So let's start with something like this. Du dt, like if I take the partial derivative of u with respect to t. Now let's take the Laplace transform of this first derivative. So if I want to take the Laplace transform of du dt, so by definition, so Laplace of du dt will be equal to integral from 0 to infinity e minus st. Now our f of t is this du dt now, multiplied by du dt. Then if I put du dt, that means I'm integrating with respect to t. So I'll put dt now. So how do we now integrate? So how do we integrate this function? So here we are going to use integration by parts. Okay. So integration by parts, we integrate one function, differentiate the other one. So I will just use the shortcut. So I will integrate this and differentiate this. I'll say let's v equals to e minus st dv equals to minus s e minus st dt. That is when I take dv dt. All right. So then my u will now be integral of the other one, integral of du dt. You know, if you integrate a derivative, it will go back to the function. So u will be u of, okay, let me say this is u of x comma t, u of x comma t. So u of x comma t, right? When we integrate du with respect to time, it will be u of x comma t. So then Laplace of that du dt now will now be what? What is formula of integration by parts? uv. This is u, this is v. That is u of x comma t times exponential minus st from 0 to infinity, okay? Minus integral of u and dv, u of x comma t, and this is dv minus s exponential minus st dt from 0 to infinity. So now when we put infinity here now, it will be 0, okay? Minus when you put 0 here, in place of time, not in place of space. This is space, this is time. So if you put 0 in place of time here, it will be u of x comma 0. All right. So if you put 0 here now, e raised power 0, that's 1. Okay. Then minus minus, that's plus. S is a constant. This is dt. S is a constant. If you bring in that s, that will be s integral from 0 to infinity e minus st u of x comma t dt. All right. So 0 minus, so it does not do anything. So I will say this is s integral from 0 to infinity e minus st u of x comma t dt minus u of x comma 0. Okay. So this is now what is here now? E minus st u of x comma t. This is like Laplace transform of u of x. If I have a function u of xt, what is the Laplace transform of this? That's integral from 0 to infinity e minus st, right? So what is here now? It is the Laplace transform of a function u of xt. Where are we coming from? We are coming from Laplace transform of partial derivative of u of xt. So when you take the Laplace transform, you are going to have it like this. So this is a s. So I will now change this Laplace transform. I will change it to big U. So Laplace transform of u of x. Let's change it to u of x comma t, then minus u of x comma 0. So this is the Laplace transform of du dt, the first derivative. All right. So sometimes we'll be solving wave equation or its equation whereby we are going to be uh, transforming second derivative. So now let's take the Laplace transform of second derivative. Laplace transform of d square u dt square. All right. So if I want to take the Laplace transform of d square u dt square using this same algorithm, so it is what? It is a integral from 0 to infinity e minus st d square u dt, right, of x comma and t. So you can be putting it or you can leave it. So then dt, because you are integrating with respect to time, we are integrating with respect to time. So let me say it again, like the whole idea of using these techniques, in partial differential equation. Now when you are solving 2D problem, you have space and time. Space is x component or y component, time is t. So Laplace transform now will be solving the problem in time components. So e minus st d square u dt square. So how do we integrate this one? Using integration by parts. Let me clean this side. Again, you say that let v, this is my v, what I want to differentiate. Let v equals to e minus st, and if you differentiate v, dv equals to what? Minus s e minus st dt. All right, this is v. Then my u will now be integral of the square u dt square with respect to time. Okay, if you integrate second derivative, it will go back to first derivative. So this one will be what? If you integrate the square u, it will be du dt, right? So now putting it into the formula of integration by parts. So I don't want to clean this Laplace transform of first derivative. So if you now put it into the formula of integration by parts, so the Laplace transform of second derivative will now be uv. This is u, this is v, that is e minus st multiplied by du dt. Now we are dealing with partial derivative, we can write it as u underscore t, right? So this is let me put it like this, u underscore t of x comma t. Do you get now? That means when you differentiate this u partially with respect to time, that is uv. Uv minus integral, don't forget you're having the interval 0 to infinity, minus integral from 0 to infinity of what? U and dv. So what is u? This is our u, this is our dv. All right, so u is a minus, oh okay, this and this, minus s e minus st multiplied by, well, du dt. Let's say, okay, let me put it like that, du dt with respect to time. Okay, so if you put infinity here now, it will be 0. If you put 0 in place of time, if you put 0 in place of time, it will be what? Or if I put infinity, why is it 0? Because when you put infinity here, e raised power minus infinity, that's 0. Okay, so if you put 0 here now, if you put 0 in place of time, that's 1. So this will be ut of x underscore t, x comma 0. All right, minus times minus, that's plus. Okay, so s will come out as constant, s integral from 0 to infinity e minus st. All right, du dt. So this is the du dt. All right, so what does this thing, what does it tell us? What is here now? It tells us that what we are having inside this integral, it is the Laplace transform of what? First derivative. That thing is just like step. If you are taking Laplace transform of second derivative, it will take it back to Laplace of first derivative. If you are taking that of first derivative, it will take it back to the original function. So what is here now? It is definition of Laplace of first derivative. Then you are now going to substitute for this. This is the Laplace of first derivative. This is Laplace of du dt. All right. So if you substitute this guy into this formula, sorry, don't mind my handwriting. So if you substitute now, you are going to have the Laplace of the square u dt square will now be ut. All right. Oh, minus is here because you are doing definite integral. So you are going to write this then minus when you put 0. So this is minus ut of x underscore t x comma 0 plus s. I'll now open a bracket. Everybody here now is this. So s big U of x comma t minus u of x comma 0. All right. So expand. So Laplace of the square u dt square is equals to, this is s square, right? Big U of x comma t minus what? This is s, okay? Minus s u of x underscore 0, and this minus ut of x comma 0. So this is Laplace of second derivative. Well, some books they will be using s. So yeah, I'm using x, so that's not a problem. Now, after knowing that, these are the main tools that we will be using to evaluate, to solve PDE using Laplace transform techniques. So in this video, we are going to be looking at wave equation and its equation extensively. So you can go back to how to find Laplace transform, shift theorem, inverse Laplace, convolution theorem. So you can just go back and review those ones before you start watching this series. So the first example we are going to solve is this. So let's solve this boundary value problem. All right, so this is an example of its equation in one dimension. So how do we solve this using Laplace techniques? So the first thing we are going to do is to take the Laplace transform of both sides. We take the Laplace transform of du dt, Laplace transform of the square root dx square. But then we are going to be taking, t is the time, x is the space. We are going to be taking the Laplace of that space as constant. So time is changing, okay? So solution now, take the Laplace transform of both sides. So you are going to say this is Laplace transform of du dt equals to Laplace transform of the square u dx square. All right. Now what is Laplace of du dt? From the first thing that I just cleaned now. So Laplace transform of du dt is s big U, s big U of what? Now what is this? U of x comma t, all right, minus u of x comma 0. That is the Laplace of du dt. Now, how do I take Laplace of the square u dx square? X is space. The space is not changing. It's time that is changing. So we are just going to say this is let's say it is big U, or let's say this is the square big U dx square of what? Let's say of x, um let's say is x comma t, all right, u of x comma t, so which represent the Laplace transform of the square u dx square. All right, so this is an unknown. If you remember, how do we use Laplace to solve ordinary differential equation in math method? If you take the Laplace transform, you do some partial fraction, then you later find the inverse of that stuff. All right, so this problem now, what is here now? This is the main unknown. This is our target. So after everything now, we are still going to take the inverse Laplace of what we later get. So putting the boundary condition, these are the boundary condition. U of x comma 0. U of x comma 0 is what? 2 sine 2 pi x. So we are going to have s u of x comma t minus u of x comma 0 is what? Oh, if I'm using x here, so I have to change this one to x. I'm using the same variable here. So this guy, 2 sine pi x, is this u of x comma 0. 2 sine 2 pi x, all right, is equals to the square u of x comma t dx square. But for the sake of convenience, you can leave that u of x comma t, just be writing u, so that we'll not confuse ourselves. Well, what we're having here is what? Is a second order differential equation. If you remember the time we were solving Euler method now, Euler method will break a PDE into two systems of either second order or first order. So this is a second order now. So collect like term. If you collect like term, we are going to have the square u. For the sake of simplicity now, I will not be putting x and t, so I'll just be putting u, big U. So the square u dx squared, bring this one, minus s, all right, u, all right, is equals to minus 2 sine 2 pi x. Do you get? So what is here now? Second order differential equation. If you solve this, oh, there is a mistake. the square u dx square. All right, yeah, we are getting it. We are getting it. So this is what second order differential equation. Then we solve this. How do we solve this? Auxiliary equation. What is the auxiliary equation of this one? M square minus s, abi, because u is this. Okay, m square minus x equals to 0. All right, so m is equals to something like this. So after getting the auxiliary equation, we find the complementary solution. So this is u, the complementary solution is equals to what? Let's say we are using c1, or let's say a c1 exponential root s x, because we are solving with respect to x, plus c2 exponential minus root s x. That is the complementary solution. Then we need the particular solution now, because we're having this is non-homogeneous. So what is the particular solution? So you remember differential operator, D operator techniques. So here I'm going to use D operator. So how do you find the particular solution? I'll turn this one to 1 over d square minus s, all right, of what? Minus 2 sine 2 pi s. And you know the rule that govern differential operator using trig function. So we are going to put the value of this 2 pi here now with minus. So the particular solution will be 1 over this 2 pi. You are going to put it here, 2 pi all square, but minus will be here. So minus s, all right, of minus 2 sine 2 pi x. Do you get? So what is minus 2 pi all squared minus s? Minus 2 pi all squared, that's minus 4 pi square. So this one will give us 1 over minus 4 pi square minus s of minus 2 sine 2 pi x. So factorize minus. So this will be minus 2 sine 2 pi x over minus into bracket 4 pi square plus s, right? 2 cancel 2. So our particular solution is what? 2 sine 2 pi x over 4 pi square plus s. After getting the particular solution, then you join them together, all right? So you join them together. So u now, the solution of this ODE, u is equals to what? Complementary plus particular solution. You add them together. U is equals to what? C1 exponential root sx plus c2 exponential minus root sx, then plus 2 sine 2 pi x divided by 4 pi square plus s. Okay, after that, c1 and c2 are constant. You remember the time we are using what do we call it, Euler method. You find c1, one will be 0, the other one like that. So what condition am I going to use to find this constant now? So the first condition we are having is oh, I've cleaned it. I think I put it here. One of the conditions are as follows: u of 0 comma t equals to 0, u of 2 comma t equals to 0, and u of x comma 0 is equals to 3 sine 2 pi x, right? I think these are the three main conditions that we have. So we have two constants. We've used this at the beginning. So we are going to use this. U of 0 comma t equals to 0. What is the meaning of u of s comma t? That means when the space is 0, and when the space is 0, the solution is 0. So if you equate the solution to 0, anywhere you see x, put 0. E raised power 0 is 1, all right? If you put 0 here, e raised power 0 is also 1. If you put 0 here, sine 0 is 0. So this one will give you equation 1, all right? Then you use the other boundary condition. U of 2 comma t is 0. It means that when the space is 2 and then the solution is 0, the solution is 0 if space is 2. That means if x is 2, if you put 2 here, this will be c1 exponential 2 root s, all right, plus c2 exponential minus 2 root x. Does that make sense? If you put 2 here now, this will be sine 4 pi. I know that sine pi is 0. All sine pi are 0. So even if you put 2, everybody here will still be 0. So this one is equation 2. Then you solve equation 1 and 2 simultaneously, okay? So from equation 1, c1 equals to minus c2, substitute for c1 into equation 2. So this will be c1 exponential minus 2 root s minus c1 exponential minus 2 root s. Oh, this is plus, equals to 0. If you factorize c1 exponential 2 root s minus exponential minus 2 root s equals to 0, right? Now, I said something in one of our video that whenever you're having something multiplied by another thing and they are 0. Now, obviously, what is here is exponential function. An exponential function starts from 1, x squared, like that, like that. So this one obviously is not 0. That means it is the c1 here that will be 0. So c1 is 0. And if c1 is 0, automatically c1 is negative of c2. c2 is also 0. c1 and c2 are 0. Then what will be our new solution? If c1 and c2 are 0 now, our solution will be what? Our solution u equals to what? These two guys are 0. Then our solution will be 2 sine 2 pi x divided by 4 pi square plus s. So what I said is that if you are solving partial differential equation, you have to make sure that you are having space and time, c and what do we call it, c and x. All right, now we're having s. Now don't forget we are using what? Laplace transform. Let me just bring an idea now. This s, what is it doing now? You know, there's something in digital electronics, there's something we call modulation and demodulation in analog and digital. If you are having, if I make a noise now, let's say I shout ah, so that my ah now, it can be like this. Let's say if you represent it on graph, it can be like this with respect to amplitude and time. Now that ah now is a function of t, is a function of time. Now when you take the Laplace transform of that noise, it will go back to a function of space, s. Now if you have a noise now, let's say you have a noise, different kind of noise, and you want to use it to form a signal, you are going to take the inverse Laplace. If you take the inverse Laplace of that s now, it will go back to f of t. That is what we call modulation and demodulation. So this s that is here now, when we later take the inverse Laplace of this guy now, it will go back to time. Then this x here will be constant as our space. All right. So that is u now. After getting u, what is the next thing to do? Then we are done. Then we need to convert it to u of x comma t. Now this u that we get here, it is u of what? S comma s. Do you get? Because the function here are x and small s. Then our solution has to be in form of u of x and t. X and t, because the each equation we are solving are in form of space and time. So we are now going to take the what? Take the inverse Laplace. You take the inverse Laplace of this guy of 1. That is, if you take the inverse Laplace of u of s comma s, it will go to u of x comma t, small letter. If this one is capital letter, please don't mind my handwriting. All these are capital letter. If you take the inverse Laplace of u of x s, it will go to u of x t. Now you will now take the inverse Laplace of 2 sine of 2 pi x over 4 pi square plus s. All right. Now, what are we changing? We are changing this s. That is where our focus will be. You see all these 2 sine pi x now, they will just be constant. Take them out. It will now be 2 sine 2 pi x dot inverse Laplace of 1 over 4 pi square plus s. And don't be scared, this 4 pi square is just a number, is a constant. Now let me go take you back to Laplace transform. If you take the Laplace of exponential at, it will be 1 over s minus a, right? Now what is here now? This 4 pi square is just a number. So if you now take the, let's say you take the inverse Laplace of 1 over s minus 3, it will go back to exponential 3t. Okay. Now take the inverse Laplace of 1 over 4 pi square plus s this time around. So this will be exponential minus, okay, minus 4 pi square t. It will now have time, multiply by 2 sine of 2 pi x. And this is our final solution now. U of x comma t. U of x comma t is equals to 2 sine pi x. You see that is having space and then is having time. We got it. So you can first go back and review Laplace transform technique before you start watching this video. So that is one example under heat equation. So let's solve a problem on wave equation now. Okay, so this is a wave equation now. So we'll take the Laplace transform of both sides. You take the Laplace transform, you take the Laplace transform, you take the Laplace transform. Don't forget that time and space, you take the Laplace transform of time, so Laplace transform of space will be unknown. Okay, so if you take the Laplace of this, the square u dt square, that is s square u of what? Well, I've said I'll be using just u. I already know that my u is what? U of x and x, all right, because Laplace of time will change to s, a function of s. Okay, so minus ut, all right, of s comma 0 minus, oh, this is minus x u of, okay, let me say like minus x u of x comma 0 minus ut of x comma 0. All right, that's how it will be. So this is the Laplace of this guy. Now, so what about the Laplace of space? So let's just say this one is d square big U dx square. So this u is the unknown. Plus, now what is Laplace of sine pi x? Now, Laplace is what? We are using what? Time. So this function of x will be constant. So for example, if you want to take the Laplace of, let's say, 2t, you can take these two out. You just take the Laplace of t. All right. So if I'm having sine pi x, so the Laplace of this will just be sine pi x times Laplace of 1. Okay. So Laplace of 1. So if you take Laplace of 1 is what? 1 over s. Okay. So this one will be sine pi s over small s. So now check the boundary condition. U of x comma 0 is this. U of x comma 0 is 0. So this part is 0. Ut of x comma 0, that means partial du with respect to time of x comma 0 is also what? Is also 0. So this part will be gone. So you are going to have s square u is equals to d square u dx square plus sine pi x divided by s. So this is the second order non-homogeneous differential equation. So bring this one and transfer sine pi x to the other side. You'll be having d square u dx squared minus s squared, all right, big U is equals to minus sine pi x over s. All right. So how do we solve this? This is second order inhomogeneous differential equation. So you find the auxiliary equation. What is the auxiliary equation of this guy? It is m squared minus s squared equals to 0. The one we solved previously is just m squared minus s. So if you solve m squared minus s squared, so m equals to what? Plus or minus s. All right, two solutions. Then you write the complementary solution. It will be what? Let's say we are using c1 exponential. The first one is sx because this is our solution. Then we are solving it with respect to space x. Then plus what? c2 exponential minus sx. This is the complementary part. Then how do we find the particular solution? Particular solution here, I'm going to use d operator. So what is d operator of this? It will be 1 over d square minus what? Minus s square. This s square is the coefficient of u. So d square minus s square times what? This function minus sine pi x all over s. Do you get? Now, we are going to, you know how sine works now. We are going to put this pi. We are going to put this pi here now. So the particular solution will be 1 over, if you put this pi here now, it will be pi square minus s square. But don't forget, d of sine as or cos as, it will have minus here. The value will have minus of minus sine pi x all over s. Okay. So factorize minus and this minus. Your particular solution will be sine pi x over pi square plus s square with s here. Do you get? So this is how our particular solution will looks like. After getting the particular solution, then you join them together, the complementary solution and the particular solution. So our u now, like our general solution now, it will be the complementary part. This is the complementary part, c1 exponential ss plus c2 exponential minus ss, then plus this guy sine pi x divided by s into pi square plus s square. Do you get? So now we need to find c1 and c2. How many conditions do we have? We have 3 conditions. We'll use this guy. We'll use this. Now, then I'll go back to this condition again. I'll go back to condition 1. Sorry, this is u of 0 comma t. U of 0 comma t, yes. Yes, u of 0 comma t. Let me check the condition again. U of x comma 0, u of 0 comma t. Yes, we have u of 0 comma t equals to 0, and we also have u of x comma 0 equals to 0, and u prime of x comma 0. Yes, u of 0 comma t is 0. So if I now use this, use the first condition. The first condition means that when x is 0, when the space is 0, the solution is 0. All right. So when the space is 0, the solution is 0. You can just underline this one. This is our general solution. We need to find c1 and c2. So if you now put x as 0 here and u as 0, so we are going to have 0 equals to, if you put x as 0, this will be c1. If you put x as 0, this will be c2. If you put x as 0 here, sine 0, everybody here will be 0. So c1 plus c2 is 0, equation 1. You see that it's having the same pattern as heat equation. Okay. So the second condition now, I will now use this. U of 1 comma t, it means that when the space is 1, the solution is 0. That means 0 equals to, anywhere you see x, put 1. If you put 1 here in place of x, so this will be c1. This will be c1 exponential x plus c2 exponential minus x. Now if you put 1 here, that will be sine pi. Sine pi is 0. Okay, so everybody here will turn to 0, and that's equation 2. Now if you solve this, this is similar to what we solved earlier on, so I will not waste time. I already know that my c1 is 0 and my c2 is also 0 when you solve this. So if c1 and c2 are 0 now, what will now be our general solution now? Our general solution, u of what? X comma s, all right, is equals to, these two guys are 0. It will be sine pi x over s into bracket s square plus pi square. So this is solution in s, like this is solution in x and another unknown function s. So how do we now transform this one to u of x comma t? Is by taking the Laplace inverse of this guy. If you take the Laplace inverse of x and s, this one will demodulate this function s, turn it to function t. All right. So then our u now, our general solution will now be Laplace inverse of this function sine pi x over something. So u, then you take the Laplace inverse. Take the Laplace inverse. Take the Laplace inverse. If you take the Laplace inverse of u, big U of x comma s, it will give you u of x comma t. Then you also take the Laplace inverse of this guy, sine pi x over s into bracket s square plus pi square. Now, how do I take the Laplace inverse of this function? You already know that everything here now, this pi x part will be constant. So I can say this is a sine pi x times Laplace inverse of 1 over s into s square plus pi square. How do we move from here now? We resolve this guy into partial fraction. You remember, we resolve into partial fraction. So resolve into partial fraction. So how do we resolve? This is 1 over s square plus pi square. Oh, sorry. It will be what? A over s. This is a bs plus c over s square plus pi square. Do you remember the partial fraction? Clear the fraction. This will be a times s square plus pi square plus s times bs plus c. All right. So if you say let s equals to 0, let this s equals to 0. If s is 0, everybody here will turn to 0. If s is 0, this one will be 0. This will be a pi square equals to 1. A is 1 over pi square. Do you remember partial fraction? Then how do we do the rest? You expand this partial fraction. So 1 is equals to as square plus a pi square plus bs square plus cx. All right. Then you equate the, if you equate the s square part, this will be a plus b equals to, this one does not have s square. You remember now, equals to 0. And your a is 1 over pi square. 1 over pi square plus b equals to 0, which implies that b equals to minus 1 by pi square. Then we need to get c. What are you going to equate again? I will equate x. If you equate x, cx equals to, we did not have any x function here. Oh, cs equals to 0. That means c is 0, right? So we've gotten a, b, c now. So we are now taking the Laplace inverse of this now. Our partial fraction is a over s. What is a? 1 over pi square s. What is b? B is minus 1 over, so plus times minus is minus. Minus 1 over pi square of s square plus pi square. C does not exist. So this one is, oh, this is having s. Okay, this is having s. You get now? That is how it will be. That's our partial fraction. Then we'll now take the Laplace inverse of this function. So if you take the Laplace inverse of 1 over pi square s, so our solution now, u of time and space now, is equals to Laplace inverse of 1 over pi square s, Laplace inverse of s over pi square into s square plus pi square. All right. 1 over pi square will go out as a constant. Laplace inverse of 1 over s over pi square will also go out. Okay. Laplace inverse of s over s square plus pi square. So what is Laplace inverse of 1 over s? That's t. Okay. So this will be t over pi square. All right. Minus over pi square. What is the Laplace inverse of s over s square plus pi square? That's cos. So this will be cos what? What is it? Cos pi and t, because a function of s will transform back to a function of t. So this is our what? This. Then you multiply it by sine pi s. So u of x comma t now. U of x comma t is equals to sine pi x into t over pi squared minus 1 over pi square cos pi t. So that is how our solution will be. So this is the general solution of this wave equation now. You see that this is space, this is time, this is space, this is time. So your solution must have. So this is another example now. Want to evaluate this first order partial differential equation using Laplace transform. So you take the Laplace of both sides, Laplace of du dt plus Laplace of what? Du dx is equals to Laplace of x, right? Now this is first derivative. If you take the Laplace of du dt, it will be x u, all right, u of x comma 0 minus what? Minus minus s, all right, x of x u minus just u of x comma 0. That is the Laplace of this time. So Laplace of du dx, let's say that one is just the big u dx, all right. X is a constant. If you take Laplace of x, no, we are taking with respect to time. We take that x outside, we take Laplace of 1. So Laplace of 1 is 1 over x. So this will be x over x, all right. Now what is u of x comma 0? U of x comma 0 is here, is 0, all right. So this will be su. Let me just say su of x comma x, all right. So xu plus du dx equals to x over x, right? What order is this one? This is a first order ODE. So I'm going to write it properly as du dx plus su equals to x over x, all right? This is what? This is a linear differential equation. How do you solve linear differential equation? Integrating factor. So what is your integrating factor? E raised to power integral of this. Eh? E raised to power integral of s with respect to x, all right? If you integrate s as a constant with respect to s, it will just be sx, all right? Then after getting the integrating factor, how do we solve linear equation? The linear equation is u times integrating factor. What is integrating factor? E raised to power xs equals to integral of this part, x over x times integrating factor e raised to power xs with respect to x, all right? So we can take this over x outside because we are integrating with respect to x, okay? If you take that over x outside, you are going to have u e raised to power xx equals to 1 over s integral of x exponential sx. So how do we integrate this? Integration by parts. I will just use shortcuts for sake of time. Here we are going to use integration by parts method. I will differentiate x, I will integrate exponential xs. If you differentiate x, that's 1. If you differentiate 1, that's 0. If you integrate exponential xs, it will be exponential xs over s. If you integrate this guy again, it will be exponential xs over s squared. Plus, minus, plus. You remember? So this is the first answer, this is the second answer. So therefore, we are going to have u exponential xs equals to this times this. Don't forget, 1 over s is outside. Let me say 1 over s into big bracket. This times this. S exponential xs over s minus this times this. Exponential xs over s squared. After we are done integrating, what are we going to put? Plus c, okay? So open the bracket. U exponential xs equals to s exponential xs over s squared minus exponential xs over s raised to power 3 plus c, right? Now divide both sides by exs. So u equals to, if you divide this one by exs again, it will cancel. U over s squared. Divide by exs, 1 over s cubed. Divide this by exs will come outside to come up, okay? Oh, yeah, thank you. X over x squared. So then this is, now c is what? C is arbitrary constant that we need to find. Use this first condition. What is the first condition? U of 0 comma t now. What is the meaning of u of 0 comma t? It means that when x is 0, the solution is 0. If the solution is 0, x is 0, this guy will be 0, x is 0. If x is 0, yeah, this will be c, right? And this one will just be there, minus 1 over s cubed. So c is equals to plus 1 over s cubed, all right? So now return it back to the solution and then take the inverse Laplace. Because this is first order, so it's not big. So u of what? S comma s you get is equals to x over s squared minus 1 over s cubed plus c. C is 1 over s cubed, all right? E minus xs over x cubed. That is our final solution. Now we then take what? In order to transform this one to space and time, we take the Laplace inverse of this guy. So u of x comma t equals to the Laplace inverse of everybody, x over s squared, Laplace inverse of 1 over s cubed plus Laplace inverse of e minus xx over x cubed. So x is a constant, okay? You take s outside, Laplace inverse of 1 over s squared, Laplace inverse of 1 over s cubed. All this one were together, Laplace inverse of e minus xx over x raised to power 3, all right? So what is Laplace inverse of 1 over s squared? That is t. So u of x comma t, Laplace inverse of this is t. This will be tx, okay? So Laplace inverse of 1 over s cubed is t squared over 2 minus t squared over 2, all right? So this is what? Unit step function. Just go back and check unit step function is in Laplace transform. So the Laplace inverse of e something like this, e minus asf of s. Go and check the how to find the Laplace inverse of unit step function. So that will be another series. So this one will be h t minus x. This h is called if side function, times t minus x all squared over 2. So that is this the inverse Laplace of e minus xx over xs. So that is how we transform this s to space and time. All right. So that is it. So thank you.